Okay, well, I hope the quiz went well for you. And we are going to continue on with some material here. Just to kind of give you an idea of where we're at, we're starting section 8.5. And this is dealing with the ratio and root test. There's also another test that's in there. It's called the comparison test, but we're not going to actually cover that in this course. And my pen is acting up here. And then after we cover section 8.5, we actually only have one more section to finish up chapter 8. But we are going to have at least one more quiz, if not maybe two more quizzes, because I find that this particular chapter is a relatively challenging chapter, and I want to make sure we get plenty of practice on the problems before we have an exam. So let's go ahead and look at the ratio and root tests here. We'll probably just cover the ratio test because of the quiz that you had today. So I'm not going to necessarily give an hour-long worth of videos here because of the quiz. So the ratio test is what we're going to start with. And so we have to first kind of get some of the rules down here first. So first off, we start with a series, and the series needs to be an infinite series but the key thing here for the ratio test is that these a sub k's have to be greater than 0 for all k. So I have to only be looking at positive terms. Now, what we're going to do is we're going to compute something here. R is equal to the limit as k goes to infinity of a sub k plus 1 over a sub k. Then there's three possible answers we could get for R. If R is between 0 and 1, the series converges. If R is greater than 1, the series diverges. If R equals 1, the test is inconclusive. And that's important to recognize here, because on a quiz or an exam, you will always be given a series that there will be some test that you can apply that will say whether the series converges or diverges. There will never be a case where you are just, I don't know which the case is. You know, if you get test is inconclusive, that means you're using the wrong test and you need to use a different test instead. Now, one way that you can determine that a ratio test often has factorials present. So before we even look at an example, I want to review factorials here, because we're going to have to be simplifying factorials. So remember here, let's just even do a simple one here. 4 exclamation point, that's 4 factorial. We know, or we should know, that this is equal to 4 times 3 times 2 times 1, which of course is 24. And then of course we can do 5 factorial and everything else like this. But what's also important to recognize is that 4 factorial, you could rewrite this as 4 times 3 factorial. Now, you might say, well, why would I do something like that? You know, why would I write it like that as opposed to 4 times 3 times 2 times 1? Well, the reason is that if you had, for instance, 4 factorial over 3 factorial, you could rewrite this as 4 times 3 factorial over 3 factorial. But then, of course, these 3 factorials would cancel out, and I'd be left with simply 4. So that's the reason we want to make sure to be able to write this. Now, we're actually going to, instead of just using the numbers here, we're going to actually probably be using variables. And what do I mean by that? Well, we might have, for instance, k plus 1 factorial. K plus 1 factorial, well, this would be equal to k plus 1 times k factorial. Man, my pen is really giving me problems today. Another one you want to be able to do, for instance, would be what if you had k plus 2 factorial? Well, you could write this as k plus 2 times k plus 1 times k factorial. And you're going to want to be able to do these kinds of rewriting these factorials, because it's going to, as we'll see here in an example second, make the simplification much easier. So let's look at an example here. This is problem number 16. Well, before I do this, I meant to mention this at the beginning of the video. I have solutions posted for all of the assignments in Chapter 8, and I actually went ahead and posted solutions for more than what was assigned. So if you want to look at more problems to get more practice, you can do that. So this is problem 16, and it's the sum from k equals 1 to infinity of k to the 6th power over k factorial. And we're supposed to use the ratio test to determine if this converges or diverges. So we're going to look at the limit as k goes to infinity of a sub k plus 1 over a sub k. And we call that r. I mean, it's not a big deal if you call it r or whatever you want to call it. So let's first just write down what these are here. So a sub k plus 1, well, I'm just going to put in k plus 1 everywhere I see a k. So I have k plus 1 to the 6th power over k plus 1 factorial. And then a sub k would just simply be k to the 6th over k factorial. And then we're going to need to do this limit now. So I'm going to compute r is equal to the limit as k goes to infinity of k plus 1 to the 6th over k plus 1 factorial divided by k to the 6th over k factorial. Now what we want to be able to do here first is we want to be able to simplify this. So what I'm going to do is I'm going to write this as limit as k goes to infinity, and I'm going to write this not in a division, but I'm going to write this as multiplication. So I've got k plus 1 to the 6th power over k plus 1 factorial times, then it would be k factorial over k to the 6th. Because when you're dividing, of course, you'd flip and multiply. Now I'm going to simplify my factorial. So I've got k plus 1 to the 6th power over, well, I'd have k plus 1 times k factorial, and then this is multiplied by k factorial over k to the sixth. And with these factorials, you should always get to a point where you can cancel the factorials out. So I can cancel those k factorials out. Then this is equal to the limit as k goes to infinity. What am I left with? K plus 1 to the sixth power over k plus 1 times k to the sixth. Now I claim that this limit's actually relatively straightforward to do, and I claim that this is equal to 0. But I'm going to go through all the details to make sure everyone sees that. So let's go through all the details. So I'm going to lit this as, Kim, limit as k goes to infinity of k plus 1 to the sixth power, and then if I multiply the denominator out, I'd have k to the seventh plus k to the sixth. Now I'm going to somewhat multiply the numerator out. I could multiply the numerator out completely if I wanted to using the binomial theorem, and I'll show you that in a second here if you want to see it. But I know that I'm going to have a k to the sixth term plus a bunch of other stuff. Because I know that my highest degree term is going to be k to the sixth, because I've got k to the sixth, but there's a bunch of other garbage here too. So it's not equal to k to the sixth, I just know that I'm going to have k to the sixth over k to the seventh plus k to the sixth. Which, because these are then rational functions, we know that they follow the limits of the lead terms. So the lead term in the numerator is k to the sixth. Lead term in the denominator is k to the seventh. And then simplifying this, I'm not simplifying it though, you get limit as k goes to infinity of 1 over k, which is equal to 0. Which then, because r equals 0, we know the series converges. Because remember, if r is greater than or equal to 0 or less than 1, the series converges. Now, the one thing I think sometimes people get mixed up is that we've used r before and the geometric series, but remember, these are completely different. These are geometric series is when you have a very special case, and as I said with the ratio test, a strong indication that you're going to use the ratio test is that there's a factorial present. Now, before I wrap this video up here, I just want to go back here and actually show you how you can multiply this out. There's something that some of you are probably familiar with, which is called Pascal's triangle here. So you start out with 1s on the diagonals, and then you get 1, and then you have, if my pen would write here for a second. Why is my pen not writing? 1, 2, 1. Because then what you do is you add 1 and 1 to get the 2. Then you have 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1, 1, 6, 15, 20, 15, 6, 1. And you could keep going down the pattern here. But if you look at this here and look at the different levels, this would be 0 exponent. This would be exponent of 1, 2, 3, 4, 5, and then 6. So if you wanted to know what k plus 1 to the sixth power is, this would be equal to 1 times k to the sixth plus 6 times k to the fifth 1 to the first power plus 15 k to the fourth, 1 squared, plus 20 k cubed, 1 cubed, plus 15 k squared, 1 to the fourth, plus 6 k 1 to the fifth, plus 1 times 1 to the sixth. And notice here that when you add these exponents up, they're always equal to 6. 5 plus 1 is 6, 4 plus 2 is 6, and we're just starting with k to the sixth, and then we just keep decreasing. And so you would actually end up getting here, if, as I said, if you did it, this would be equal to k to the sixth plus 6k to the fifth plus 15k to the fourth plus 20k cubed plus 15k squared plus 6k plus 1, which you can see again the highest degree term, which I wrote up here, is just k to the sixth. And again, you can kind of tell that just by looking at here. Well, you know you're going to have k to the sixth power, so you know that's going to be the highest degree term. Plus, yeah, there's a bunch of other gobbledygook here, but because I'm doing a limit, I don't really need to care about that stuff. But this is actually what it would be. And this is called Pascal's triangle.